I hope it's visible to everyone. So welcome to this talk, which is supposed to be on uses of deep learning and artificial intelligence in the field of agriculture or precision agriculture. I'm Rahul, as Dr. Arun said that I am research scientist at Pixel and also affiliate researcher at Monash University and working on a research project at CSR IIT Bombay too. So starting with a very boring slide about the motivation, like whatever we are talking about, ultimately where it is going to help. So of course, we all know that world population is increasing and that demands more food production. But unfortunately, the techniques which we have, the existing techniques which we have, suffers from operational efficiency, less operational efficiency, and sustainable practices are also getting reduced, which is ultimately impacting the climate change in a bad way. So whatever we are doing in field of precision agriculture or increasing the efficiency of it is basically we are trying to optimize the central part, which is those practices, how we can improve so that ultimately they take more input resources. The side effects of those activities should be less on the environment. So in a way, it should less contribute or not contribute to the bad behavior of climate change. So what we are going to discuss about some aspects, how deep learning or AI can be used for scientific farm management and optimal use of these input resources which we give in agriculture. And we can do it, of course, by the engineering solutions, IT-based solutions to reach to the sustainability of this system. Okay, going ahead. So the question is why we need this deep learning thing. We were already working with the ML techniques and image interpretation techniques. So why there is a need of deep learning in agriculture? So of course, there should be some bottlenecks with ML techniques, existing ML techniques, or even image interpretation techniques, which DL may be able to solve, which researchers are continuously trying to identify. And given the fact that agriculture is a kind of a very noisy environment in a sense, where we will get first sparse and limited data, and second thing is very noisy data. But if we have a lot of data, then whether these DL techniques can be that much reliable to create a repeatable models or not. So those kind of applications we will see in this presentation. And ultimately, of course, not only looking into the crop stress or crop properties, but also with DL can be take some decision making farm activities, so that kind of a complete loop can be created. First observation or data collection, and then decision making based on the observations. So a little bit of background I will start with. So if we see, then green evolution in agriculture started around 1960s. By the time it came to India, it took almost 10 years or 15 years, 15 more years. But in general, it started in 1960s, where we focused more on mechanical aspects of agriculture using heavy machinery and all. And then by 1980s, biotech revolution came up, where we focused more on like high yield giving seed varieties, which can also be used in Indian scenarios or any country specific climate. So that kind of biotech revolution came in 1980s. 2010, a digital revolution started happening, but I still say it was in latent stage. It was there, but not evident that much. Maybe more on a research level, or very few organizations or institutes were doing it. And then, like most of the deep learning aspects in agriculture, if we check the literature, then we will find that most of the papers it starts coming after 2015. Of course, there are papers before this, but like majority of them starts coming after 2015, which uses deep learning techniques in agriculture. So the topic which we are going to discuss is quite new, not very old. So we have kind of limited examples in that sense. So before I start discussing the uses, we should have an overview of what is precision agriculture, where these techniques can be used. So this is a precision agriculture cycle, where we can see there are 3 steps basically. One is data collection and processing, where we can use multiple platforms to collect these data set. And then data interpretation and decision making step. So whatever data we have collected, we have to kind of extract information from it. So second step is that. And the third step is, of course, taking corrective measures, because whatever we have seen and we have analyzed, ultimately we have to take necessary action or corresponding action in the farm. So, and this is a kind of cycle. Again, we will do corrective measures in the farm, and then we start collecting data again to see whether whatever we did in the farm has made some positive change or not. And then again, data collection, analysis, corrective measure. And in each of these steps, we can use artificial intelligence or, of course, deep learning techniques in very specific manners. So starting with the data collection and pre-processing step. So if there are n number of things which we can do in this, so I will take examples like if we have a ground sensor, then there are examples like deep learning based weather forecast model. So even Google weather forecast, I learned that it uses machine learning model. Of course, not right now deep learning, but machine learning model. But there are a few papers which uses deep learning models to predict weather for next 7 days or so. Of course, not in a annual basis, but in a kind of very short future time interval. Another example of uses of deep learning is when we collect any data set. For example, let us we are collecting using drones, so we can make autonomous drone flights which are capable of kind of finding its own path depending on what it is seeing, so on ground, of course. So there deep learning can be used. We will have few examples of that. And if we have ground related, we want some ground related data, then of course there are robots which are autonomous in nature. They are trained on a lot of farm images and videos, so that they can kind of navigate in the farm very easily. And other aspects in this are, of course, like data pre-processing, which is a part of data collection in a way, from raw data to at least usable data creation. So in the pre-processing also, there are some steps which are kind of integral to deep learning aspects, because at some point of time, we have to also do the data cleaning, making it into specific size of pixel images. So of course, those parts are there, but they are also equally valid for any other artificial intelligence techniques. So starting with some of the examples in this particular section. So this is a weather forecast model by Hussain et al. So here we can see what they did is they took historical pressure, humidity, and temperature data from a state of US, and then compared the results against a neural network model and a deep learning based stacked denoising autoencoders. And here we can see what they got is, if we see the red line and this green line is original and red line is the prediction of the deep learning model. So in graph we can see they are pretty close to each other with respect to the blue line, which is predictions of neural network. And in terms of RMSE error, they also found that SDAE was performing more than 2 times better than normal neural network. So in this way, it has increased the deep learning has increased the efficiency and accuracy. However, the same model has to be validated for other regions with more data set. So, but the point is, it is being used, and till now it has shown a very positive effect. Another example of deep learning based autonomous drone flights here is, this is also for data collection, of course. So in general, right now, if we make a plan, autonomous drone flight plan, then we put the waypoints and the drone flies on a specific pre-decided path, right, in a serpentine motion. But what about if we want to search something, but we don't want to kind of scan whole farm? So the training of this drone flight can be done in such a way that we decide, okay, you have to start here from here and end at here. And then in between, based on whatever you are seeing in your field of view, you have to decide where to move in order to get my target objects quickly. So even there is a pre-decided path, but drone moves in an autonomous way based on pre-training things, and then identify a specific plant or some object on ground. Maybe if required, collect data from there, maybe images from there, collect images from different angles of that from there, and then come back to the waypoint where it is supposed to be getting landed. So like that, there is another use of deep learning in this case. This so for autonomous bots, where these bots are kind of not aerial bots, but on ground, and these are very, very useful because ultimately they give us a ground truth information. Right now, if we want to go and collect ground truth, then it is labor intensive, time consuming, and of course sometimes not even possible in many scenarios. So these autonomous bots are kind of able to navigate through farm, and they are being trained. There are already existing bots in farm which can do these things. They can click images. They can also sample some soils. And for example, some of the use cases can be pest information. Once they click the images, they can analyze it. However, right now we are only discussing about the data collection. So the point is, these autonomous bots, they can be used for data collection without any human intervention. Another interesting paper which I found related to data collection using deep learning was root and soil segmentation using X-ray tomography. So these guys used these X-ray tomography images of bare soil where all these roots and soils are mixed, and then they used a deep learning model to kind of identify what are those which are roots and not soil. And as we know that root and soil can get mixed and they may look exactly similar, but with some kind of specific wavelengths, they can be identified. So there are research being done on that. However, what I believe, these kind of research may take a lot of time because, of course, there is a very costly and very risky sensors involved in it. But from an academic perspective, I guess it's good to look from all the direction of a problem statement. All right, so coming to the second part of the precision agriculture cycle, which is data interpretation and decision making. So majority of the paper which you will find in this particular sector will belong to this particular category, where deep learning are used for identifying something or counting something. However, some of the papers also focus on kind of yield estimation or soil moisture, and as we see, weather forecast. But almost 60% or even more than that, I will rather say, belongs to just identification of some aspects. And maybe the reason is the IT guys or the computer science guys, the core domain people, they use the deep learning mostly for those kind of activities. Even the open source data sets which are there, they are based on identification of something or counting of something. And in this also, like 60% of the papers which you will find is using the CNN architectures like AlexNet, VGG16, or Inception, ResNet. So this is very kind of a still not very diverse options or things which we are able, algorithms which we have right now, which are being used in agriculture. But uh, as I said, there is a lot of work has been done in this particular section. So one of them are weed identification. Either they collect high resolution drone based um, ground based robot images, so that they have very clear view of what is on the ground, and they identify weeds or distinguish weeds from the actual crop. And then of course they will take necessary action to only pluck out those weeds or put some pesticides on that or something to just destroy it. And then flower tassel counting, again, this is, if you see the things, then some identification is happening in this also. Like we can count from images, we can count the flowers, tassels. Plant recognition, what kind of plant on ground, these things are of course possible from uh, high resolution images, but there are papers which also use airborne, like manned aircraft or even satellite based images. Another example is plant phenology recognition, at what stage the crop is, where the crop is going in the flowering stage or maturity stage, how delayed it is. And those kind of information is of course useful if we get it beforehand. Then crop type classification, very much explored topic from the satellite images, because this kind of information is used as a kind of baseline to do another second level of study. Once we know what crop type is on ground, then we can then estimate their chlorophyll or water content or yield. But if we don't know what crop is there, it becomes very challenging to talk about that in a holistic way. Soil moisture, very important. So land cover classification, crop biochemical properties, we will see some of these examples. Then crop biophysical properties, yield estimation. Yield estimation is particularly useful because ultimately, if we know what amount of yield I'm going to get after 2 months of time, then we can decide the price accordingly, or government can decide how much things they can export, or whether they have to import or not. So if you get lead time of 2 months or so using very advanced algorithms, so of course that helps in management and planning. If there is any disease or not from images, people are trying to identify using deep learning techniques. Fruits counting, similar to kind of flower or tassel counting. So let us see some of the examples of deep learning in this sector. So last, in data collection also, we saw that there are bots which can autonomously visit in the farm and keep collecting images wherever they see a potential to collect image. So this bot is developed in 2019, and what it does, it just keep moving in the field, take images, and then analyze those images to identify the kind of weed information in the farm. Another example which uses YOLO V4 algorithm, where top of the canopy drone based images for this is for maize crop is being used, trained, and then the flowering or number of flowers is being counted. Kind of a very, one of the kind of challenge in these areas are still like the false positives. If any area which is little more brighter or looks like a bright spot, they can also be get identified as a flower or a tassel, specifically in maize, field of maize tassels. However, that can be updated with more data or more representative data. But at the same time, for deep learning, that's the kind of a bottleneck right now in agriculture. We always have noisy data set, and it's very difficult to kind of annotate and give a ground truth information. Anyway, another example is potato disease classification. Like, you have images of leaves of potatoes, and then we can tell whether it is this disease or that disease. And all these models basically will need a lot of images as an information, kind of labeled images, and then the model will get training. For in the field of crop biochemical properties, let us say I'm giving example with hyperspectral data, because earlier we were seeing the RGB, so basically it is happening in terms of spatial domain, but there is also one aspect of deep learning to be applied in a spectral domain of the data set. So each pixel is having maybe 200 bands or 400 bands, depending on which sensor you are using. And of course, as we know that each of those features on the ground will have different spectral characteristics. So deep learning models can be trained, their hyperparameters can be identified, what they are going to give weightage to which particular parameter. And we can identify also which bands are more important for a specific crop property. And we will get this kind of map. This is created from Average images, where we can see for different fields or farms what kind of chlorophyll information, higher or lower. So anything which is green, bluish in nature, which is, I guess, in this section you can see easily, or even greenish in nature, they are moderate chlorophyll value. Blue is higher chlorophyll value, and whatever in red you are seeing is the low chlorophyll value. So based on that, crop biochemical properties can be identified using deep learning models in a better way. Of course, there are machine learning models also, but what we have seen or what we have observed till now, that with good data set, deep learning model gives lesser RMSE and better accuracy. Now coming to the corrective measure stage thing. So of course, now we have collected data now and also analyzed where the weed or where, like, what kind of intervention has to be done in the farm. So now there are bots which can actually do those intervention in the farm. They are autonomous robots which scans the farm. They know how to move. They know where, if I find it there, then okay, I have to go and pick that fruit or that particular weed, or they have to drop something. So they are very autonomous in nature, and people are working on those kind of projects. Another is the spraying using drones. This image is taken from a Japanese farm where you can see this particular helicopter can kind of lift a heavy amount of pesticides, and of course they can do this spraying in farm wherever required. However, this kind of technology are like still not using the deep learning exactly, but they're moving towards it because of course whatever challenges we are facing with existing technology. And we can also kind of create where more deposits of these pesticides has happened or where less has happened, and then compare it against uh, our treatment plan, which we got after the image interpretation or data interpretation step. Another examples of some bots which are already in market, of course not in India, but in US markets, are these farm bots. They call it harvesting bots too. They are kind of autonomous in nature, and companies are desperately trying to make them very autonomous in nature. And of course, the way forward for them also is the deep learning algorithms. Let us see a case study now for AI in agriculture, where what we did is we flew a camera on a drone with over a maize farm, and on the, like, in terms of cameras, we had hyperspectral imager, RGB images, and we, of course, as we have hyperspectral images, we will get kind of this kind of data cube after pre-processing the data set. And from RGB images, we can stitch these images easily, and these images are kind of leaf level information of the farm. We also collected ground truth data. So now we have remote sensing drone based data, and as a ground truth data, we did the destructive sampling of leaf and identified the water content using oven dry method and nitrogen content based on the CHNS analyzer. We also use the handheld hyperspectral spectroradiometer. So there are drone-based hyperspectral data, handheld hyperspectral data, then ground truth. So all these data set will be used for training artificial intelligence model. Now, RGB data was used to create the 3D point cloud to estimate the crop biophysical properties, like we can identify height, we can identify biomass, then leaf area index. And the hyperspectral data was used for estimating the bands or indices for leaf water and leaf nitrogen content. So all these are till now still we are identifying it using some techniques, identifying some informative bands using some artificial intelligence techniques. And then once we create our model, then we can get a kind of a height map like this of the farm, LAI map like this, where we can see if it is blue in color, then LAI of those areas are higher, and if it is kind of orangish or yellowish or even greenish in nature, then for these areas LAI or biomass will be lower. Another product which we got is a generic crop stress. So this is a kind of interim result of the models, where we can see the temporal farm map, and we can also see what are those areas which are more stressed or less stressed. And then finally, we can also get information about leaf water content at different growth stages, leaf nitrogen content also. And then by combining these maps, we can also identify those areas which are either or and water and nitrogen stressed. So once we have these kind of information from the farm, then of course it's little easier to do the intervention in those areas, maybe by flying a drone with a pesticide tank over there, or sending a farm robot to do some activities. Now, the future opportunities of deep learning, of course, in agriculture, like very less amount of work has been done in these sectors, where like seed identification, people are coming up with this, like I have not found a very clear-cut paper on seed identification. However, in phenotyping, they do have something related to it. But I guess deep learning has to be implemented in this, which has a good potential. Now, of course, soil and leaf nitrogen content, as we saw earlier, that AI has been used, but to do these things, but not the deep learning. So there is opportunity for future researchers for applying the deep learning techniques to get the soil, leaf nitrogen content, and irrigation plants water stress detection, and so on. Water erosion assessment, of course, this can be a very good project based on satellite imagery or high resolution drone or airborne imageries. Identification of contaminants, disease or defects on food. So agriculture like go in parallel with the food industry. So in lab applications of these data set, using deep learning can be very useful. Crop hail damage. So generally people are doing it with image interpretation techniques. Many insurance companies are interested in it. It will be good to see how deep learning will change the game here with by giving better accuracies. Greenhouse monitoring, of course, now estimating the growth of plants, trees based on previous consecutive observations, right? So so all these things are happening right now, and mostly people are using general artificial intelligence and machine learning techniques. But the point is, what we could achieve only a limited accuracy with that. Maybe it is due to the data limitation, but I guess now the world is moving towards kind of data intensive farming, where they're putting a lot of sensors also in the field. So I'm quite sure in coming years we will see deep learning based applications. And then replicating crop and soil physical processes. This is very interesting because right now people are not looking towards deep learning from that perspective yet. They just think that we will have data set and we will train it. But I guess the kind of simulating these physical processes of soil and crop based on some simulated data itself, but if we can use them as a training a deep learning model, because this is a very complex kind of relationship between environment, soil, water, and crop. So if we have even simulated data sets, so can we use the deep learning models to understand this behavior and then ultimately implement it in field? Of course, the calibration will happen with real-time data set, whatever we will be collecting. But almost no work has happened in this particular sector. People are not just focusing, which is a very having potential of use of deep learning. One of the example which I want to show here is Singapore indoor vertical farming. So this is basically a future of farming in many aspects, because what these guys are doing is, so since it's indoor, so they can control the lighting, they can identify the growth of each plant using their imaging techniques. They can control it even. So they have basically huge amount of data set which is basically telling them how the crop grows with given input resources. And all these data set will be ultimately used for creating a model and predicting about future crops. So this kind of data set will, of course, will be using the deep learning models. And once we create a better model, then we will be knowing what will happen with 80% or 90% accuracy, and we can take those decisions beforehand. Before kind of occurring that problem, we can take that action. So this is very fascinating field which is coming up in recent future. Now, some of the bottlenecks of this deep learning in agriculture is, as we discussed, that they need large data set to train. Otherwise, if we just give few data set, then the models will be limited to only those observations. So, and it's very difficult to get, especially in the kind of field scenarios, difficult to get all possible combinations of it. But of course, it is what it is, and people are training it, but that's of course a bottleneck. Data annotation is of course a heck of a challenge, because it's extremely annoying and time consuming to sit and annotate your target objects in an image. And that also creates bottleneck, because that's a manual effort which goes there, and wherever there is manual effort, there will be error at some point of time. Even missing data, we don't have continuous data for agricultural environment. Sparsity of the data, and given that it's spatio-temporal, we are not talking about a point-based information or one image information. We are talking about an area over a period of time. So these create kind of challenges for these models. Data is always noisy, always. We will never get very clean data set. That's the kind of behavior of agricultural data. But I guess that's a challenge, and there are techniques using which we can remove these noise. But ultimately, like normal AI guys or computer science guys, they also tend to work with the raw data itself, because they believe that the deep learning models has to be fed with the raw data in order to they can understand what is the kind of relationship. So there are some latent features too, latent features of, like in the field of agriculture, which generally these images or these data set can't capture, but they're still there. And if we don't incorporate those latent features, then the decision or the identification, whatever happening, that may not be that correct. And those latent, for example, if we are collecting just top of the canopy images, of course we will have images, but we will not be using sunlight information. So in future, like researchers should incorporate those information also in their models, uh, because they may be latent, but they are very useful information. Curse of dimensionality in case of course, hyperspectral that comes, there are ways to remove it. And of course, boundaries of data set expressiveness, whatever data you give, that kind of result you will get. However, there are kind of a transfer learning now happening. People are retraining their model, which are already trained on some data set, right? Cat, dogs, cars, like those kind of data set, which are already in open source. And then your model will be kind of already identified features from there, but with some small amount of data set, which may be about the fruit counting or flower counting. And with those small training set, your model can work better. So right now, I guess that's how people are doing things. And that's where the limitation of the accuracy is happening. We need to work a little more on that. And of course, there do not exist like a lot of data set which is available in open source, so that researchers can work. It's very difficult to kind of go in farm and collect data set. Only they can do who have funding, who have resources, but like who are not involved in those kind of projects, it's very difficult for them to go and do the research. And most of the AI guys, the core AI guys who actually builds these algorithms, they are not from agricultural background. So this particular kind of disconnect between the use and the creators also is very relevant in this case. So I guess if the more data set is available in public domain, then that will enable even the coders or the creators of these techniques to work on that specifically. On that note, these are the list of publicly available agricultural data, which you guys or whoever is listening to this presentation can go and check these, download them, and implement their models, their deep learning models for various purposes. They are very diverse data set, and I guess that that will help them in understanding the agricultural behavior or properties, and ultimately help the society, of course. So yeah, I am open for questions now. Thank you. I am seeing one comment, like how much flexibility in DL model for agriculture means. Can we use a particular model for different state like Haryana and Pune or India of India? Right. So I guess this is very relevant question. This is about the repeatability of the model. If we train a model on a specific location data, then what is the chances that that model will work for other geographical locations? So actually it depends on what kind of data set you are working with. For example, if we are trying to identify, let us say, fruits, So generally the shape, size, texture, or these properties of, of, of an apple, let us say, will remain more or less same. The only thing which may change is the background. On which you trained your data set. So let us say you collected your data somewhere in Kashmir, and then there the background and those things, because you have to crop those fruits to annotate. So if there you have a lot of difference between this particular geographical location and your other geographical location, then it may lead to lesser result in that sense, lesser accurate results in that sense. But generally people have tried it, and for fruit detection, flower detection, they were quite okay, given the limited data set which they have. But let us say now you are collecting hyperspectral information. So what happens if I am in the southern part of India? Then southern part is generally little warmer than the northern part of India. During winters I'm talking about. So if you are collecting in January or February in southern part, so your atmospheric interference with your data set will be different than if you collect data in the northern part in the same season. And that's where your data is changing. So logically, we should first kind of remove these atmospheric effects from the data set and then implement our algorithm. But I have not seen people focusing from that direction till now. So in that way, your model may fail or may give kind of worse results if you change your location. So the idea is, or the logic here is, your model will work at different locations given we have controlled or we have identified or removed effects of other parameters which may impact the data set. I hope that answered your question. If not, then please put things in chat. Another question is, can you please tell whether there is any available data set and the most popular architecture? So yeah, there are a lot of available data sets, as I showed in my previous slide, which is, oops, this one. Most of the data set is, you will get is kind of images of some leaves or crops where they are counting something in a sense, like either counting something or identifying something. For example, the disease image, there will be images of leaves with some spots on it, and the deep learning model will be able to tell, oh, this is due to this particular disease. People are using YOLO a lot, YOLO v4, for identification of these. Of course, YOLO is faster in that sense. So yeah, I guess that answered your question. Where's the chat box?
Rahul, 1 second before going to the next session. Thank you for the wonderful presentation. For going to the next session, I would like to thank Professor Adinarayana sir for gracing this workshop by his presence. Thank you very much, Adi sir, for your kind. You taking out time for being in this workshop. Thank you again, and we are really blessed to have you here. It's really inspiring us. Thank you very much, sir.
My pleasure, Arun. My pleasure. I always, I'm with my students and then, want to see Rahul plus one day. So that's what I'm seeing it now. Thank you very much. Yeah.
Thank you. Thank you so much, sir. Thank you.
Thank you. Yeah.
Yeah, just adding to that, Professor Adinarayana is my PhD guide. He's still mentoring me even after my PhD. So I'm glad he's here. Yeah.
Yeah, please. Sorry for interrupting, Rahul. Please go ahead. Thank you.
Yeah, I'm not seeing any question right now. Like,
I think Sangeeta ma'am raised her hand.
Yeah, please go ahead.
Hello. Yeah. Good morning, Dr. Rahul. Yeah, I have one question. Like you mentioned, in the future opportunities, the disease and defect detection in maybe food, or we can say fruit. So currently, I'm working on thermal imaging based quality inspection of the fruits. So I'm just have a curiosity to know that how we can actually have an amalgamation of thermal imaging plus hyperspectral and spectroscopy, so that we can get more like how we can use those things together, so that we can have a very good like results for both like disease detection as well as the quality checking for the fruits, basically in Indian scenario. So can you suggest, or what is your opinion on this?
Right. So I guess there are two parts of it. If the quality check is there, then is that quality check is happening on field, or that quality check is happening once the fruits or the grains come in some warehouse or storage place. So if it is happening in the storage
It is
place,
both. It is, yeah, it is both on site as well as off site.
okay, then I guess there should be a two dimensions of approach which we should apply. If it is in a laboratory environment, then that makes life a lot easier, because the environmental effect under which the data will be collected, we can control it, and that will lead to a better models and ultimately better results. Thermal is very good in that sense, because thermal can tell us kind of uh, if due to any internal rottenness uh, or anomaly in a crop or a seed or a kind of those grains, then the temperature will be of course different. And if it is in lab environment, then we can control the ambient temperature, and then we can collect these thermal images. That will of course lead to more informative data set. Hyperspectral, of course, is useful, but unfortunately, hyperspectral cannot penetrate up to like few micrometers of the top surface. So, if the effect of rottenness or any quality degradation has lead its effect to the top of the layer, then hyperspectral will be, of course, useful in that sense. And generally that happens in a sense we cannot see from our naked eye, but the effects are also on the top surface as on the leaves. So the collection of data set in a very controlled environment will give a better kind of uh, model. And now once we understand the relationship between, let us say, the temperature, the surface temperature, and the problem with the crop, or the hyperspectral signatures and the problem with the crop in a controlled environment, then this knowledge transfer has to be done to the field. Because when we will go to the field, the first thing which we will face challenge is we can't control the sunlight, right? And even we can't collect data as per our wish. Like we can't collect data from top of the canopy, let us say, because fruits will not be visible. We have to move in a sense horizontal. If that is the case, then all those BRDF effect, which is coming due to change in sun angle, change in camera angle, lighting effect, those has to be first removed from the data set, and then we can apply some algorithm which are already trained in the control environment here. And then of course over a period of time, once we understand, okay, what are the kind of algorithms which works and why they work, based on which bands or what are those features which contain more information, and then we can keep reducing it or making it more narrower towards a specific data. It may be just thermal, it may be few bands of hyperspectral, or if we can collect the lidar data, then lidar is also useful in that sense for some cases. So there are, I guess it's an active research area, and a good amount of research planning before data collection has to go there. Yeah, I'm not sure if I
Thank you.
said that.
Thank you for your inputs.
Thank you. I guess there is a question. Can you please tell any work data set? Multispectral images used next. Yes, multispectral images are quite they are cheaper than hyperspectral camera. So I guess most of the people are using multispectral images. You will get a lot of multispectral open source images from some softwares which process these airborne images. So they put these some example data set, as well as there should be many GitHub repositories which uses multispectral data set. So multispectral data is easier to get. Yes, there should be. I guess in some of the links which I have shared, it should be there. If not, then you can email me later. I can send you the link to those data sets. I guess that's it.
Okay, I hope we don't have any more questions, and I hope that if they have any further questions, you won't mind in answering them through email. I hope they are free to contact you through email and other.
Sure. Sure.
Thank you again, Dr. Rahul, for taking time and kindly agreeing to deliver this talk. It was actually a very interesting talk, and I hope participants are able to correlate this session with the previous sessions, and really thankful for taking your time. Thank you again. And personally also, it's actually very glad moment to see you after a short interval.
Yeah.
Thank you, and thank you all participants. Thank you.
Thank you for inviting me, and thank you all the participants.
And participants, so we'll have our next session at 10:15. The next session will be chaired by Dr. Nikhil Tripathi. Dr. Nikhil is my colleague and an expert in cybersecurity area. So next session will be chaired by Dr. Nikhil from 10:15. Thank you all.